Okay, I would like to talk about the analysis of the large-scale turbulent structure around the inline array of the building. My name is Michioka from Kindai University. In background, investigating large-scale turbulent motion within a large canopy is very useful for understanding the polygon removal mechanism from the urban canopy, like this. No. Our group we implemented a large eddy simulation for turbulent flow using a regular array of the cube like this. So this is a movie for the 3 miles velocity fluctuation at the street side. Red represents the high speed motion, blue represents the low speed motion. As you can see, the large scale, high speed, and low speed motion periodically appear at the street side. At another case, our group also implemented a large simulation for turbulent flow around the inline array of the cube, like this. This is also a movie for the 3 miles velocity and vector around the inline of the cube. As you can see, the high speed, large scale turbulent motion, large scale so low speed motion as generated near the side of the cube. So in previous study, large-scale turbulent structure as observed within the idealized urban canopy and around the inline area of the cube. We also we observed rough structure of the large-scale turbulent motion, but detailed spatial structure of the large-scale turbulent motion are still unknown. So in this study, to capture the structure of the large-scale turbulent motion around the simple building geometry inline around the building like this, proper orthogonal decomposition POD and spectral POD as applied to the time series of velocity obtained by LES. The data of the LES for turbulent flow around the inline of the cube like this. Please check the detailed complement condition in this paper. Cube height is 0.05 meter and the cube was set on the bottom surface at equal interval h. Approaching flow is uniform laminar flow. To exclude the effect of the approaching turbulence on the turbulent flow around the cube. So turbulence flow is generated only by cube in this case. So this is the energy spectrum of the streamwise velocity fluctuation at the side of the cube. This energy spectrum has a peak at the frequency 0.03 like this. This peak is observed after Fifth Canyon. These peaks corresponding to the large-scale turbulent motion. So to capture this large-scale turbulent motion, POD and spectral POD were applied for 3 horizontal cross-sections and 2 vertical cross-sections. 3 horizontal cross-sections are at the Z by 8, 0.25, 0.5, 0.75. And the 2 vertical cross-sections are both sides of the cube, y by 8 minus 0.75. Data as 10,000 snapshot, and the time interval of each snapshot is 0.004 seconds. I briefly explained the POD. The POD decomposes the random velocity fluctuation into a set of the POD modes and their corresponding time coefficient, like this. eigenvector POD mode and eigenvalue of the covariance matrix of the velocity fluctuations as obtained from singular value decomposition SPD. Snapshot POD also get the same result. The eigenvalues correspond to the contribute of each model to the turbulent energy. Eigenvectors with a higher eigenvalue mostly correspond to the large-scale turbulent motion. If you are interested in the POD, please refer to this paper. Here is the eigenvalue at each POD mode. As you can see, the first and second eigenvalues are almost identical. And the shape of the time coefficient of the first and second POD mode are not completely sine function, but very roughly the shape resembles the sine function. And its corresponding frequency is roughly 0.03. This frequency corresponds to the energy spectral peak. So the first and second POD mode are roughly in pair and correspond to the large-scale turbulent motion. So I will show you the first and second POD mode in the next few slides. This is the first and second POD mode for streamwise velocity fluctuation U dash and spanwise velocity fluctuation V dash. For the horizontal cross section at z by h is 0.25. The length of structure is approximately 6h, and pair of the high speed and low speed motion appear alternatively in the streamwise direction. Within the area enclosed by red line here, positive spanwise flow is generated between the cube. Conversely, within the area enclosed by blue dot line, negative spanwise flow is generated between the cube. This means that when a pair of the high speed and low speed motion is a pair of the both sides of the cube, spanwise flow is generated high speed motion to low speed motion like this. At every area I showed. So large scale turbulent motion strongly affects spanwise flow between the cube. Next, at the middle of the cube, right, distance to 0.5. At the middle of the cube, almost same structure are observed at the near the surface. Streamline structure nearly interact with the spanwise flow between the cube, like this. However, after the Tate Canyon, streamline structure become weak. Next, at the upper location, Z bar H 0.75 near the cube. As you can see, the slightly longer structure approximately from 6 to 8H appear. Because the mean streamwise wind velocity is faster than the mean velocity near the surface. So these structures are elongated in the downwind direction by faster mean velocity. In addition, these structures mostly interact with the spanwise flow between the cube. So these large-scale structures are very important for the environment between the cube, maybe elements. Next, I will show the first and second POD mode for the vertical cross section at the both sides of the cube. Y by H 0.75, 0.75. As discussed earlier, near the bottom surface, the pair of the high speed and low speed motion are appears alternating. And near the top of the cube, pairs are elongated in the streamwise direction and become large. So they look like a structure entitled to the right to up. So large-scale turbulent structure is captured by POD, but these POD modes may not exactly represent the structure at non-fixation dimension, no, non-dimensional frequency 0.03. This where the energy spectrum has a peak. So to capture the structure at this frequency, spectral POD is applied. So I skip the detailed, okay, I skip the detailed explanation of the spectral POD, but spectral POD captures the structure in each mode. Here is the spectral POD, SPOD mode energy, and SPOD has multiple peaks on these frequency. I visualize SPOD mode here. In this study, I focus large-scale turbulent motion, so I will show the spectral POD mode at this frequency. Here is the spectral POD mode at this frequency. So I will show the first POD mode. So as you can see, the first POD mode are quite similar to a POD mode. So in present case, the first POD, first and second POD mode mostly capture the structure at this frequency. So this is the conclusion. POD and spectral POD applied to time series velocity obtained by large distribution for turbulent flow around simple field. At the first second POD mode, near bottom surface pair of the high velocity structure and low velocity structure regularly appears in streamline direction on the all sides of the cube. The streamline size of this structure is approximately 6h, and this structure is strongly linked to the spanwide velocity between the cube. At the head increase, large-scale turbulent structure become large. In the present case, the first and second period node are similar to the first period of this frequency. Thank you.
Any questions? Yeah, maybe I can answer. Okay. Yeah, I do the similar areas, so I have some questions. First of all, what's the mass resolution for actually your research? The mass resolution to resolve the cubes.
Mass resolution.
The mass resolution. How many you are using the large edge simulation? So which kind of method? Finite volume method or finite difference?
Finite volume method.
So how many cells to resolve each cubes?
40. 40. Yeah.
Oh, okay. So what's the subgrid model used in the large edge simulation?
Subgrid.
The subgrid scale model.
Dynamic smoothing model.
Dynamic smoothing. So, how do you control the usually dynamic smoothing model may induce some variation because the simulation, the subgrid model may not that stable. So how can you keep the simulation stable to not dump down during the simulation?
No, I didn't do anything. Yes.
The dynamic smoothing scheme use the original average or local average for the coefficient of the model.
Yeah, you are right. But in this situation, no local average. Local smoothing constantly is used.
Okay.
Okay, just more one question. Okay, thank you.
Thank you for the presentation. My question is regarding the use of this POD for large-scale structures visualizing. So, what is the advantage we are getting from this using this POD as compared to, for example, using a two-point correlation method to visualize the large-scale structures?
Oh, two-point correlation. I did the two-point correlation.
No, like I'm saying, is there any specific advantage with using POD method for a two-point correlation?
So I did catch it.
There is advantage between the P and BOB and the spatial correlations between the two points.
Oh,
Sometimes you have been too square.
yeah, but POD has a yeah, POD gets a many structures. Yeah,
Nice.
yeah.
Thank you.
Thank you.